Good morning. To start today, I just want to point out that assignment 1 is formally assigned tomorrow, and all that means is instead of a class session, you can watch a video going over the assignment, which has not been posted yet. You can see the link there is hidden still. That's because I still need to record it. I'm going to do that later today. But you can start now, but it's just the idea is the class time tomorrow can be used to start working on it. The PDF goes over the parameters of the assignment, and then the video will talk about just how to finish it, how to do the quiz, submit the work in the Dropbox, and so on. So everything is there to get going, and so I highly recommend starting that tomorrow. The other thing about it saying being formally assigned tomorrow means that it's due 2 days from that, 2 weeks, sorry, from that date. So in this case, Friday, February 11th. All right, so let's jump into today's lecture material, where we're going to finish up chapter 9. Last class, we went over the terminology and theory behind decision trees, which, as mentioned, are going to be an important, what we'll consider a basic modeling technique. So in other words, an individual type of model that we're going to use to build other models, as we'll see through aggregation. So what we're going to work on today as a way to motivate some of the other topics related to this is through an example. So let's consider an illustrative example. Illustrative here being a bit of a pun because we're going to look at a lot of images as we go through this. It's a very visual example, which is nice. And what we're going to look at, I find this example interesting because it's not the kind of thing you might expect to work well here with this modeling technique. So we're going to look at an example of curve reconstruction. And I'll explain why I made that comment here in one moment after I outline what we're going to do. Okay. So the example that we're going to look at is the following. We are going to have a single feature. So, and let me just get the setup here. So for we're going to generate 50 data points. For I equals 1 to up to 50 set. So we're going to generate 50 target values, y sub I, and the y sub i's are all going to be identically independently distributed. So there's no dependence between any of them. And the way they're going to be distributed is they're going to be given by a normal distribution. And the center of this normal distribution is going to be the sign value of the feature xi. So xi here is just going to be a numerical real variable with a standard deviation of, say, of sigma squared. So what we're doing here, all this is a sine wave with a Gaussian noise term. Okay, so there's what we're doing is we're taking feature values, the feature here just being a real variable, and computing its sine, the sine of it, sin being the sine function, the trigonometric function. But the idea is the points, the y values, so are not going to lie perfectly on the curve. So this is what we mean by introducing some normal Gaussian noise, right? So they're normally distributed around the mean. So the idea is that most of them are going to be close to the curve, but they're going to move away from it in a random but predictable, well, sort of predictable way. They're going to follow a normal distribution. Okay. All right, so why do I say that this is a weird, or perhaps a kind of example you might not expect this modeling technique to work on? Okay, so think about, so we defined decision trees last time. What are we doing? We're essentially what we're doing is a finite number. We're answering a finite number of yes or no questions. Right? So these are the splits. We're splitting into two parts based on some aspect of the feature that provides a good splitting rule in the sense that it reduces the overall predictive error of the model, the sum of squares error. But what are we looking at here? Well, we're looking at what you might think of as a sort of continuous problem, right? So we're taking the sine curve. The usual sine wave is a continuous smooth function of a real variable. And so the idea is we're going to have a point cloud generated by this process. We're going to have 50 points, which don't exactly track the sine curve, but move away from it, off of it in a normal, following a normal distribution. And the idea is, if we were given that point cloud, would we be able to recover the sine curve through it? And so this seems like, in some sense, like a very continuous or smooth type of problem, and perhaps not the thing that would be well suited to this kind of approach, where what we're doing is looking at just binary answers in a sort of discrete way. Okay, how is a finite number of sort of yes or no splits going to reproduce something like a sine curve in an adequate way? And what we'll actually see is it does a reasonable job, with some obvious limitations. Okay. And so what we're going to start with is about the simplest thing we can do. So we begin by building what we call a decision stump. That's the name. The name is intended to invoke the idea of a very small tree. And what is this? It's a decision tree with a single split. So we take all the training data, whatever that is, and we split it once into two sets. Okay. So we'll see an image of what this is in a moment. Let's describe what's going to happen. So in this example, the whole idea here is we set up an example where the feature space is relatively simple in terms of the number of features. It's just a single numerical variable. There is only one feature x, namely the independent variable on the horizontal axis, the x-axis. Okay. So last time we described what happens, how do we answer binary yes or no questions with numerical variables? And the answer is we split on yes or no, does a value satisfy some inequality? So we find an inequality to create a split in the values of that variable. Okay, so as we'll see in a moment, we're going to look at an image of this tree. The optimal splitting rule here is, it turns out to be, is x greater than or equal to 3.1, yes or no? So we split on the answers to that question. Okay. And a little note here to kind of indicate why this is the case. Now, the whole point is the decision tree algorithm can discover this by trying other sort of splits. Now, what it's going to do is it's going to attempt a certain number of splits because, well, theoretically, there's an infinite number of possibilities because we're talking about a real number variable, right? A continuous variable on the x-axis. So you could only assess a certain, you're going to have to tell it how many decimal places to check or something like that. Okay, but little note, right? What's the theory that is explaining why this split happens? Well, pi, the real number pi is approximately 3.1416, right? Something like that. Sine of pi is 0. Okay. So what we're going to see is essentially we're splitting at the point where the values of the sine function are most changes from positive to negative. And in the case of our sine function, our curve with noise, most of the points on one side are going to be positive. Most of the points on the other side are going to be negative. Okay, and we'll see this in a moment. All right. So then what happens? So this partitions the x data So in other words, the horizontal axis into two nodes in the tree, so the stump. Okay. For each node, we compute the average response value. Okay. So in other words, we have in our data set, we have so we said xi run, well, we have the xi's and the yi's, right? Each data point is a pair as I runs from 1 to 50. So some number of those 50 data points are less than 3.1 in the x, some are greater. And then what we do is for each of the ones who are less, we group all those in one node, all the ones greater in another node, and we look at the y values that we generated using that normal noise, and then we average those together. So we compute the average response value. So in other words, average y value for points xi, yi in each node. Okay. Oh, sorry, the parentheses should be right here. All right, okay, so that's just a description of what's going on, but all of this is going to make more sense, I think, if we look at it. Okay, so let's take a look at the images. So let's see. This then is what happens when we generate the, do I have, oops, sorry, let me make sure I've got the right image here. Yeah, I missed one. Yeah, I did. Okay, so here's what the stump looks like as a decision tree model of the type we've seen before. I hadn't loaded this one. Okay, let's take a look. There we go. Okay, so what's going on here? What do the numbers mean in this? So the first node where it says 100%, what that's saying is we have 100% of the data, all 50 data points that we generated. And what the negative 0.026 means is that's the average y value of those 50 data points. Now, one way to think about this, if you're familiar with the symmetries of the sine curve, its average value over the interval 0 to 2 pi, so 0 to 6.3 approximately, is 0, okay, by symmetry. Now, of course, we don't expect to get exactly that in this case because we generated 50 points with some noise added to them. And in this case, what we see is that the average value of all the data points is close to what the theoretical value should be. It's close to 0. But then what happens when we split on the yes or no question, is x greater than or equal to 3.1? If the answer is yes, the x value is greater than 3.1, that consists of about 51% of the data points. So a little over half of them generated had that value for x. And the average y value of those data points is negative 0.67. On the other hand, if we split those 50 data points, well, we split on and to no, that's about a little less than half of them, 49% of the 50 data points. The x value is less than 3. What does the no mean here? It means the x value is less than 3.1. Okay. So in that case, those data points had an average response value of 0.64. Okay. So overall, the average was close to 0, but when on the split now, we've split them into a highly negative and, well, in a relative sense at least, a fairly negative and fairly positive node, right? The two response values now are almost negatives of each other. Okay, but the decision tree itself, the tree diagram doesn't show all that much. Let's see what it actually does in the context of solving the problem, so reconstructing this curve. So here's what our decision stump created as a model. Okay. So we see here we've got this cloud of points generated, and we fit this curve, which is the blue curve here is the actual sine function. So this is the exact graph of the function y equals sine of x. That's why we call it the truth. So this is the blue curve is what we're attempting to reconstruct iteratively through this decision tree. The red curve, where it says decision boundary, that's what we actually generated. Okay? Because remember, what we do is we split the data into two nodes, and the split occurred at 3.1, indicated here where that black arrow is. And in each of those nodes, what we took as our prediction was just the average of all the response values. So in the first node, we average everything together and get 0.67. That's the red line between 0 and 1, the red horizontal line. In the second node, we average everything together and get negative 0.67. That's the red line in the right-hand side of the picture between 0 and -1. And then we join those together with the vertical line to join the two predictions to kind of create a continuous curve. Okay, so what can we observe about this? Well, it's a very crude reconstruction of the sine curve. Certainly, it doesn't include any of the variation or any of the smoothness or anything like that. But it's not bad. It's not. If for instance, if the sine curve was pretend that the points are some kind of maze or forest, and you're trying to walk through it. And let's say that the sine curve, the blue curve, is the optimal path to get through. If you took the red path, you've done okay, I would say. Well, I mean, of course, we could try to measure that using some kind of error, but the basic idea here is that even this very simple model does at least a somewhat adequate job of what we're asking it to do, which is try to kind of approximate this blue curve. Okay, but we would definitely like to do better than this. So let's go then from a stump with this single split to a bigger decision tree with more splits in it. Okay. In other words, split again. Okay, so x, the horizontal axis value, is still the only feature. So what we're going to split on is in each node, we're going to split on an inequality that subdivides that node best into yes or no. Are the x values greater than this value or not within the node? And the idea is that when we do that split, the yes or no answer, what it's trying to optimize is that all of the x values for yes, their y values are as similar as possible. And all the x values for no, their y values are as similar as possible. So the idea is that the algorithm, CART, remember that's the name, classification and regression tree, the actual implementation of the decision tree idea, what it will do is it will find the optimal split using sum of squares error to assess how similar the y values are. So in the way we described last time. So all the theory that we talked about last time is happening now in the background of this example. So we'll find the optimal split in each node. All of which will be, all of which meaning all of the splits of the form. So what our splits are going to look like is x greater than or equal to some constant c, yes or no, for various values of c. So it will find the best, the optimal values on the x-axis at which to split. Okay, so in our example, what happens with 3 splits? So if we create a depth 3 decision tree in our example, okay, well, here's what that decision tree will look like. So notice that the top, the first split, is our decision stump from a moment ago. Okay. Now, if the x values are greater than or equal to 3.1, so that's the left-hand side, what the algorithm figures out is that the next best split is on the question, is x greater than or equal to 3.7? And in the case of yes or no, we see then that, notice the percentages are the percentages of the whole total. So the 51% that were in the first split, the yes split, 42% of them get split into yes again here, and their average response value is negative 0.77. 9% of the total, so of that, so a much smaller chunk of that 51%, get the answer for those is yes, they're greater than or equal to 3.1, but no, x is less than 3.7. In other words, it's between 3.1 and 3.7. And their average response value is negative 0.21. So the initial split, having roughly equal sized nodes, that was actually just related to the fact, the symmetry of the sine function itself. Now we're seeing imbalances in the node sizes, right? And then finally, we split each of those again. And we find, and then similarly on the other one, on the no question for x, if x is less than 3.1, then the optimal split ends up being at about 0.52. And then that splits into two imbalanced nodes, one with many more entries than the other. And then those split again. And so then at the bottom, now we have 8 different nodes. So what's going to happen is we're going to try to reconstruct the sine curve using 8 constant predictions, constant line segments, horizontal segments, and then we'll join those together at the decision boundaries, at the point where the yes or no question is being asked. Okay. And notice then that the different nodes at the bottom here have varying sizes in terms of the total percent of the original data at those nodes. In particular, the far kind of edge ones are much larger than the others. So one has 30% of the data, and the average response value is close to -1, it's negative 0.95. And similarly, the other one has response value average 0.85, so fairly close to 1. That's 28% of the data. Okay, what does this look like in the context of our example? It's the following. So, think about it this way. The nodes are essentially the pieces of the horizontal axis, so the kind of sub-intervals over the horizontal axis, over which we have the constant horizontal line segments. So then you can see why some points contain many more, or some of them, the nodes contain many more points than the others, because you have a much longer horizontal line segment. You have a bigger sub-interval, longer interval. Roughly speaking, what's happening is the sizes of these subintervals are corresponding to the steepness of the sine curve, where its slope is greatest versus where it's less. Because if it's not changing very much, then the generated points are pretty close to one another in response value, or at least relatively so. And that's where we get those constant sections near 1 and -1. And those are near the peaks and valleys of the sine curve. It's local maxima and minima. So some of the calculus sort of theory in the background here is what's driving what's going on in the splits. Okay. All right, so the end result with a depth 3 tree is we have tried to approximate the sine curve using 8 pieces, and they end up looking like this. And so I would offer that this is not a bad attempt at reconstructing the sine curve, given the process that we're doing. All we've done is we've answered yes or no questions at 3 levels. It essentially answered 8 questions and created these 8 nodes. Yeah. Not something that necessarily we would think would be great at reproducing a smooth continuous curve like this, but it does an okay job. So thinking about it, like I said earlier, if the blue curve here, the sine curve itself, is the optimal path through a maze of these points, and we took the red path, we've probably done reasonably well for ourselves at some level. Okay. So you might ask, well, okay, can we do a little bit better? What if we did 4 splits instead? Maybe that'll get us a little closer to the curve in some of the places where we're kind of far off from it. Right, so this then brings up a natural question: is how far should we go with this? Why did we stop at 3? The question to ask then is how deep? Remember, depth through a decision tree is the maximum number of splits. So in other words, we want to talk about controlling that and choosing that depth. Okay. Well, too many splits, so in other words, if the depth is too high, what ends up happening here is the tree gets too complex, and that leads to our familiar problem, overfitting. The tree starts to chase data. Okay. You get nodes that are too small that contain, say, only one data point or two data points, or maybe even no data points is possible. So nodes contain too few observations. So the model, you can think of it as chases points. It gets locked into y values coming from various points, and that's what happens. Okay. All right. So what happens if we try to generate an overfit decision tree here? So we consider, say, the following decision tree where we see a large number of splits. So this tree has depth, say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, like depth 16 or something like that. I lost count trying to count through it. But, so you can see there's lots of splitting levels. If we try to find the longest path down, there's going to be a lot of splits. Okay? And there's not always a split at every level for every node above it. But this is what we end up with. So this deep decision tree. Now, of course, you probably can't read this because the image, you'd have to zoom in a lot. And all the nodes at the bottom are going to be almost unreadable because they're so jammed together. Many of those nodes contain just, say, 1 or 2 or even 0 data points. Okay. What's the result of creating a decision tree like this on our modeling problem, our actual attempt to fit to the sine curve? So just before I do that, let's go back to our depth 3 tree that we said does, even though it is simple, but does an okay job of describing sort of the sine curve, the blue curve. Okay, what happens with this overfit tree that we just generated? What does it look like? It looks like this. And I would argue that this is a much worse job, does a much worse job of describing the blue curve than the simple one we just saw. We see how it's chasing individual points, right? So notice, say, that big spike to a point above 2. Okay. What's happened is that point has a much different response value than the ones around it, so it ended up in a node by itself. And so then the model chases it up and immediately goes back down. Well, that is certainly not even close to the value of the sine curve at that point. So if we think about this as trying to be a path through this maze, well, we're taking all kinds of useless detours, right? We're going up to some tree in the maze, and then just immediately realizing we went the wrong way and then going back. So we wasted a bunch of walking time. Okay. So this is the problem. This is a great example of how overfitting will present itself, right? Lots of variation in the predictions because of chasing after individual points and values in the target data. Okay. So clearly we don't want something like this. Our first tree, maybe our depth 3 tree, maybe was a little too simple and we could do better. But we see at some point we've gone way too far and we're getting some really bad model out of it because of the overfitting. Okay, so with that in mind, let's talk about general approaches to dealing with overfit decision trees and avoiding them, and then we'll see how they apply in our example. Okay, so there are two main approaches to avoiding overfit decision trees. They're called early stopping and pruning. All right, so let's describe these. Okay, so early stopping, how does this How does this work? Right, so here what we're doing is we explicitly limit the growth, in other words, depth, of the decision tree. So as the name suggests, we stop growing the tree at some earlier point. Okay. Now, this method itself there's multiple ways of doing it. There are, in this case, two main ways to implement this. Okay. And the first is to explicitly restrict depth. Okay. So what we mean here is, okay, so the idea here is that depth is a decision tree hyperparameter. Okay, so how deep the maximum depth of the tree it's a decision tree hyperparameter. So set a value for the maximum depth. So essentially say you set a bound that says the tree can't grow more than this depth. Okay. And then and stop splitting if this depth is reached. Okay. And then you can try, because it's a hyperparameter, you can tune it, say, using k-fold cross-validation and try to determine what your optimal maximum depth is. Okay. The other approach is minimum node size. So here what we do is we set a lower bound. So maximum depth is like setting an upper bound, right? You're setting an upper bound on the number of splits. Here we set a lower bound on the number of observations in terminal nodes. Okay. So the idea here is if we stop splitting, if any additional split would create nodes having too few observations, so less than this minimum node size. Okay. This is also a decision tree hyperparameter, and so it can be trained. All right, and so then you want to think about the bias variance trade-off here. Okay, so in terms of the bias variance trade-off, And this is something, the relationship between the depth of a tree and whether it's high bias or high variance is something that's going to be important, especially in chapters 11 and 12. Okay. So if we have low depth and or large nodes, and of course these two things are typically going to correspond together, this corresponds to high bias and low variance. So for instance, with our decision stump or our depth 3 tree, that was a high bias model in the sense that the actual predicted values often were very different than the data points, right? But it was low variance in the sense that it was fairly simple. There wasn't much change as you move, you creep around, you move around from one X value to an X value close, the predictions don't change very much. Okay. On the other hand, high depth or small nodes, and these again correspond. If you create a high depth tree, like our overfit tree with say 16 splits, all those nodes at the bottom, we couldn't read them, but most of them, as we saw, only contain say 1 or 2 data points, and we saw that from looking at the effect on the model. So this will create a model with lower bias with very high variance. And so we know that as we go from low depth to high depth, then we're going to go from a high bias, low variance model to a low bias, high variance model, and vice versa. So then the directional arrows here, those are the bias variance trade-offs, right? So as you go from one to the other, you see which one's increasing, which one's decreasing. And so because these are hyperparameters, they can be tuned to try and optimize this, to get the minimum, to find the optimal spot in the bias variance interplay in the trade-off to get the lowest overall error. Okay, there's another approach which has some similarity to our idea of regularization in the sense of we approach sort of controlling what's going on by imposing some kind of penalty or cost. And this is pruning. Okay. So what we do with pruning is we grow a deep, almost certainly overfit decision tree, such as our example that we looked at. And then, as the name suggests, and of course the name is another one of these terms we're using sort of tree-type terminology, we prune it back into we'll call into an optimal subtree. And so, as the name suggests, as the process suggests, by prune it back, what we're going to mean is, of course, cut off branches and they're cut off leaves, right? Cut off branches and leaves. So in other words, remove nodes and branches from the tree. And that's how we get a subtree, okay? So the subtree here simply means that it's a subset of the original tree. But of course, optimal is playing a big role here. So anytime we ask a question like this, it's obvious. The obvious thing that comes to mind is optimal how. So we're going to talk about something being optimal, and we better describe how we're saying that it's optimal. Okay. So what we want to do is we want to minimize sum of squares error plus some parameter times some number. Okay, so what goes into this? What's this vertical bar t? Okay, so this is simply the number of terminal nodes. So in other words, we're making it more expensive, so to speak, and it's a cost or penalty. We're penalizing the model for having more terminal nodes. And then alpha is some sort of complexity, so cost complexity hyperparameter. So the idea is that alpha is making it more expensive, or penalizing us, so to speak, penalizing it more expensive in terms of error to include more terminal nodes. Okay. So the idea then is that as the tree grows, and so as the tree grows, as we make more splits, anytime we make a split, another split, we're going to end up with at least one more terminal node at the end. So as the tree grows, in other words, the number of terminal nodes increases, the reduction in sum of squares error must be greater than the increase in alpha times the number of terminal nodes. Okay. And so the bigger alpha is, the more we're penalizing by creating new terminal nodes, so the more we're requiring a bigger reduction in error. Whereas a small value of alpha is saying that we're not going to penalize too much by adding in terminal nodes, so we don't need as big of a reduction in error to allow ourselves to do that. And that's why it's a hyperparameter. So to identify an optimal subtree, we perform a grid search testing models across a range of alpha values, using, say, k-fold cross-validation. Okay, so let's see then the effect of these approaches on our models. So how does early stopping and or pruning affect the curve reconstruction example? Now, one other point about early stopping. We described two ways we could do it. Explicitly restricting maximum depth or setting a minimum node size. And these are both hyperparameters, and it's fairly common to use to impose both of them, to set a maximum depth and a minimum node size. And then, of course, you can train these across some grid search, or you can, and so on. You can tune the hyperparameters across the grid search. Okay, so what's going on here? There's 9 models indicated here. Now, in the first column, or the left-hand column rather, we have maximum tree depth equal to 1. So in all 3 of these are the same because all 3 of them are just the same decision stump. And then the minimum node size aspect doesn't come into play for any of those because the nodes are so big already. Each of them has about 25 points in them. Okay. But now let's consider the middle column. Here, what we've done is we've set a maximum tree depth of 5. So we're only allowing 5 splits. Okay. But then, what are the 3 rows? The first row is setting a minimum node size of 1. So in other words, as long as there's something in the node, that's okay. But in the second row, we're setting a minimum node size of 5. So there has to be at least 5 data points in that node, or in other words, over that subinterval. And at the bottom, we're setting a minimum node size of 15. Okay. All right. So looking at the top one in the middle column, here we see that the decision tree is already overfitting at 5 splits, right? So we're getting some nodes where there's a single point and it's chasing those points. And so we see, for instance, that big spike, upper spike to the point above 2 on the left that we observed earlier in our overfit tree, that's already there, even at 5 splits rather than the big number of splits that we used. Okay. But now, as soon as we impose some minimum node size restriction, all those big spikes go away, because now the model is not allowed to chase a single point. We still do see some fairly fast variations, especially kind of over the middle, where the sine curve is at its steepest in terms of slope. But then if we go down to the bottom and we set a minimum node size of 15, well, there we see that now there's a lot less of those quick up and downs, right? Because we're forcing there to be a decent number of points in each node, and then averaging those together gets us a lot closer to the one next to it, and so forth. So, for instance, the bottom model in the middle column, I think, is quite good in terms of an attempt to reconstruct this sine curve using a decision tree approach. And notice there it's only depth 5, so there's only 5 splits. But by having a reasonable depth, not too big, and then also having a good minimum node size, we avoid the overfitting problem. And yet we also get a model that is quite close to the actual values. Now, the right-hand column, it allows us to make deep trees. So the max depth now is 15. And then we see that if we don't set a minimum node size, we get an extremely overfit tree. So the top right, that was our example from earlier, our deep overfit decision tree. So 15 splits with no limitation on minimum node size. What that does is it allows us to chase points all over the place. And so we get this really overfit model. Now, by using 15 splits, but restricting the minimum node size to 5, we do much better. There's still it's still fairly high variance though, see, because there's the values can change very rapidly. Then if we go to minimum node size 15, a lot of that still high variance goes away. I think it's a legitimate question as to which model is better in the bottom row, the one in the middle or the one on the right. And offhand, I mean, there's no indication here of the overall sum of squares error. In both cases, it should be fairly reasonable. Certainly, both of those models are better than any of the other ones in terms of doing a good job of reconstructing the curve without too much error from overfitting. Okay. So this is a good example then of how we can manage the bias variance trade-off in a model like this through careful examination of the hyperparameters and tuning. How about pruning? What if we take, let's say, a really overfit decision tree like the one in the top right, and we introduce a penalty parameter, different values of alpha, and we prune it back and try to find an optimal one? So here it turns out is the optimal pruned decision tree for over some grid search. We don't have the actual values of alpha used here, but if we do tune the model on the left using and include this penalty parameter for number of terminal nodes, we get this picture. And so what I would suggest is that the model on the right is fairly good in the sense of not being too complex, so not being too high variance, but also doing a reasonable job of fitting the curve. If you were to say, if just going back one more time to my kind of made up fanciful description of this as a path through some forest maze that you're trying to find, if someone created the red path as a reasonable way through it, that's not hard to follow, but also does a good job of finding the optimal path, I think most people would agree that it's pretty reasonable. Would it be better to follow the red path on the right here, or say one of the ones in the bottom right here? that's debatable. The ones here certainly are more complex as a path, but perhaps the overall distance is shorter. You stay closer to the optimal one. So these are the kind of sort of qualitative examinations we can make. And well, we could certainly, if we had all the data in front of us, actually examine this from the perspective of total of sum of squares error, and so on. Okay, so the long story short then of this example should be that a single decision tree is actually a reasonably useful modeling approach, even for problems where it might not seem like it would be that useful. But actually, as it turns out, a single decision tree is not an exceptionally powerful predictive model. Later, we'll see that if looking at the Ames housing example, which we've talked about before, and which is the subject of assignment 1, a single decision tree doesn't do a great job on that model compared to other options. But the decision tree approach, nonetheless, will be very useful for that example and others. So, to wrap up chapter 9, let's talk about, for decision trees, some advantages and disadvantages. Okay. So advantages. Well, decision trees require little to no data pre-processing. They can handle numerical and categorical variables equally well. So in particular, I'll mention that. So they handle categorical features well. So we don't need to encode categorical features for a decision tree. They also handle missing values automatically, which is quite nice. So this is an aspect, of course, of data pre-processing that we don't need to deal with, or data cleaning. Often with lots of types of models, say you're trying to do just say a linear regression model and you're missing values, well, you're going to have to find some way to fill that in. But in this case, they handle missing values automatically. What the decision tree will do, it'll simply create a missing class, and then it'll fill out into those. Okay. Outliers, individual outlier data points don't tend to bias results too much, as long as we don't chase them, right? So as long as we don't build deep overfit trees. So outside of overfitting of overfit trees. And they don't have strong assumptions. Remember, we said that this is a non-parametric model, so it doesn't make assumptions about what the modeling function should look like. So we don't need to make the kinds of assumptions that we do for linear regression, where we have to assume a linear fit, no correlation, all those kinds of aspects. The decision tree process can be used there without too much trouble. Okay, so what are the disadvantages? Some of these are what I've already mentioned in the context of our last example. They don't have, and also in the context of the Ames housing example. As we'll see, they don't have great predictive power. One of the reasons for that is that the simple yes, no binary splits result in rigid decision boundaries. So in our sine curve, right, there, as an example, this modeling technique really can't recover the smoothness, right? You're never going to be able to split the decision tree and recreate the smooth aspect of the curve. Okay. And although we saw that we could at least make some improvements, the bias variance trade-off is not easy to control. One of the reasons why is there's just not enough hyperparameters to begin with that are there, and the ones that we have, we saw that like by playing with them, we were able to improve things. But generically speaking, when we grow deep trees, we get high variance overfit models. And when we grow shallow trees, we get high bias, simple, weak models. They're just not predictively all that useful. Okay. But as it turns out, there's an elegant solution to this problem that works in both cases and allows us to work with both deep trees and shallow trees depending on what we're trying to do. And the solution is to generate what are called ensembles. Okay. So what we want to do is we will build predictive models, powerful predictive models, by combining decision trees. And the way we're going to do that is in chapter 10, we're going to introduce the concept of bagging, which is essentially a way of creating lots of decision trees using the bootstrapping process. And from those, aggregating the results together. And as we'll see, this is not an especially complicated process, although it can, of course, become computationally difficult. But then does a really good job of creating better model out of than single decision trees. But as we'll see, there is a big limitation there that we have to deal with. And then the solution to that will be to introduce an additional level of randomness, and that will take us into chapter 11 on random forests. And random forests are going to show us how to build extremely powerful predictive models using as our starting point deep overfit decision trees. Then in chapter 12, we're going to switch gears, and we're going to ask the question, well, can we build powerful predictive models by combining shallow, weak decision trees? And the answer is also yes. That process, in some sense, it's sort of perpendicular. It's sort of at perpendicular orthogonal angles to the random forest one. That's called gradient boosting. And so we have these two sort of approaches that are kind of, like I said, orthogonal to each other, yet both of which result in powerful overall predictive models. So that's a little preview of what's to come. Let me just I don't want to get too far into chapter 10, especially because not a lot of people are here today. But let me just point out what it is, and we'll kind of start fresh on it mostly on Tuesday. So chapter 10 is on bagging. Okay. And this AKA bootstrap aggregating. The idea is to use the bootstrap resampling process to generate lots of models and then to aggregate the results together. Okay. So that's essentially the definition of the term. When we talk about bagging, what we mean is aggregating often meaning averaging in the case of numerical, but also we can aggregate together the results of categorical predictive models as well. So aggregating the results of bootstrap resampling. Okay. So what I'm going to do is, like I said, I'll save the details for Tuesday. But to wrap up, let me introduce the philosophical idea. Where does this concept come from? Why is sort of aggregation of individual results a worthwhile thing to pursue here? And where this comes from is what's called the wisdom of crowds effect. Okay. So the idea here is that large, diverse crowds often produce better aggregated predictions than any single member of the crowd. Okay, so an example of that, just kind of one of the most basic sorts of examples you can think about, is that, say, just guessing the number of, often we use beans or marbles or jelly beans, so the number of beans in a large jar. Okay. And this is, I mean, a common thing you'll get like at fairs and other kinds of sort of community events, etc. Individual guesses are often way off the mark. Now, of course, once in a while you'll get someone who gets, say, lucky and they get very close, but typically speaking, you're not going to expect most people to be able to get very close on this kind of question overall. But the average of all guesses tends to be quite close. Okay, assuming you have enough guesses. Okay, and so this is why I underlined two words in this. So large. So we need enough individual predictions. If we don't have enough, then aggregation isn't going to do too much. Okay. Now, how large is large? Well, of course, it depends. It's totally contextual. Okay. What do you mean by diverse? Okay. Well, the guessing the number of beans example doesn't really matter that much here because there's not really, most people don't have any particular sort of bias towards the high end or low end on this. And that's why what's going to happen, why is it, once you got enough guesses, why is the average guess going to be going to be pretty close? Because a lot of people are missing, but there's no kind of bias towards the high side or the low side. Some of them are guessing too many, some are guessing too few, and those errors are essentially averaging out. Okay. But in other contexts, when we say diverse, what we mean is that the predictions being aggregated do not have forms, have obvious or have significant correlations, is probably the best way to say this, in their biases. So the crowd has to be diverse in some sense in terms of perspective on the problem or on the question, on the question that we're trying to predict the answer to. Okay. So an obvious example here, well, I won't try to write anything down, but suppose if you asked a large crowd, who was going to win, say, the Super Bowl, okay, the National Football League championship game. Well, if that crowd is mostly fans of one of the two teams in the game, you're going to get probably a lot of bias in your answers in one direction. Right? On the other hand, if your crowd is very randomized, then that might not happen. Okay, so you've got to watch out for when we talk about diverse. What we're talking about is, in some sense, what perspective the people in or the different models or whatever we'll call them are being aggregated are bringing to the question. Okay, so the term wisdom of crowds, the idea, of course, has been around for a long time, but the term was popularized and perhaps even coined by a writer named James Surowiecki, whose background is writing about finance and business. And he's a very good writer. I highly recommend reading his work. You can find him online. In his book of that name, The Wisdom of Crowds. This is one of my favorite books. I highly recommend it if you're looking for some kind of non-academic reading, but I think is very interesting. So here's a little plug for the book. Here's where it looks like on Amazon. It was written in 2005, but a lot of the examples in it, I think some of them are maybe a little out of date, but the generic idea behind it, I think is still very applicable. And you might find it interesting. I certainly did. One of the things he does is explain when the wisdom of crowds breaks down. So what happens, where are there failures? Where has aggregation created very failed predictions? For instance, financial market bubbles is a good example. And why does that happen? And often it's this lack of diversity problem. Everyone in it is in attacking the problem is coming from the exact same perspective. And so this is the creation of financial bubbles is a great example of what happens in that kind of case. Anyway, so if you're looking for some reading at some point, maybe over the summer, I highly recommend this book. So that's all for today. We'll pick up on Tuesday with the bagging process, explaining how it works and how it improves our results over individual decision trees.